Hello, fellow Masters of Wine students. My name is Sabrina Lewick, and I am the instructor of Enology at the Institute for Enology and Viticulture at Walla Walla Community College in the United States. I've been teaching wine science for 8 years, and I received my undergrad degree in Enology and Viticulture from Cornell University. I love to teach, and I love getting a little bit dorky about wine science. So today's goal is an overview of sulfur dioxide in winemaking in the context of what you need to know for the Master of Wine exam. The goal is to address the kind of questions that you're going to get and to figure out really the stuff that you need to know, and to develop some vocabulary so that you can confidently discuss sulfur dioxide on your theory papers. So here are a few questions that were on exams. Explain recent changes in the use of sulfur and sulfur dioxide in the vineyard and cellar prior to the completion of malolactic conversion. Consider the implications of reducing levels of sulfur dioxide in post-malolactic conversion handling and bulk storage of still wine. And many winemakers are reducing the levels of free and total sulfites in wine. Consider the role of sulfites at bottling and until the wine reaches the end consumer. What are the implications of reduced levels of free sulfites? So something interesting that I'm noting here is that almost all of these questions deal with sulfur dioxide concentrations and also the impacts of their levels in the wine, specifically in reducing them, which is a trend in modern wine production. So everybody remain calm. You don't need to be a wine chemist to discuss cause and effect or identify and discuss recent trends in wine production. One of the nice things about sulfur dioxide is that it's actually a very simple molecule. So I think that discussing cause and effect is going to be a little easier than you think. Let's start out by discussing the what and why. What is sulfur dioxide, or SO2 as it's more commonly known? This is a small molecule with antioxidant and antimicrobial properties. And if you take a look at our little diagram here, you see a single sulfur molecule in the middle there, and it's double bonded to 2 oxygens. This is a really small molecule, and that's one of the keys to its properties. When it acts as an antimicrobial, frequently it can slip right through the cell membrane and disable a cell. I'd say kill, but more technically it disables it and kind of puts it to sleep. Why are winemakers using SO2? You're going to hear me say the word we quite a bit here. I myself make wine with our winery college cellars. So when I say we, I'm asking you to get into the mind of a winemaker and think of why we would do the things we do. So SO2 mainly is an antimicrobial compound. It combats microbes at multiple winemaking stages. Earlier in the process, it can also be used as a way of giving a competitive advantage to our preferred microbe, Saccharomyces cerevisiae. Almost all yeast and bacteria, or actually I shouldn't say almost all, really all microbes are impacted by sulfur dioxide. However, spoilage bacteria and yeast are more heavily impacted, so this is a positive thing for us. Small levels of sulfur dioxide used up front can support our preferred Saccharomyces population. And during the life of the wine, including the aging and bottling process, it's used as an antimicrobial and antioxidant compound, fighting off other things that we don't want. Sulfur dioxide is also an antioxidant. It binds with hydrogen peroxide, or H2O2. And hydrogen peroxide is formed when oxygen enters a juice or a wine. So when we have air contact of juice and wine, the oxygen goes into it and then it forms hydrogen peroxide. Sulfur dioxide actually doesn't react directly with dissolved oxygen, which is kind of a bummer for us as winemakers. However, we have other techniques of dealing with dissolved oxygen. What sulfur dioxide does is it binds directly with hydrogen peroxide, and it stops the hydrogen peroxide from being an oxidizing wrecking ball in our wine. That hydrogen peroxide can go about and oxidize different compounds. Like, for example, it could go and react with an ethanol molecule and turn it into acetaldehyde, which smells like bruised apple or nutty or sherry-like. Additionally, one of the nice things about sulfur dioxide is that it can bind to certain compounds called carbonyl compounds. That is more of a geeky piece of information. You don't need to know that word. But you can know that adding sulfur dioxide can minimize oxidized aromas in wine. So that sulfur dioxide can actually bind directly with that oxidized smelling aroma called acetaldehyde, and it can make it go away. Another reason we use sulfur dioxide is enzyme deactivation early in the winemaking process. So a reminder, an enzyme is a protein that catalyzes a biochemical reaction. So basically it makes reactions in the wine go faster. And in a lot of cases at crush and press, the reaction is the browning of small phenolic compounds. So the addition of sulfur dioxide deactivates these enzymes and stops these reactions from happening. So there's two main types of enzymes that are present for browning at crush and press of white wines. One is called polyphenol oxidase, and if you've ever bitten an apple and left it on the counter, you'll see that that bite mark goes brown. That's the same thing that happens in our juice during crush and press. This enzyme is browning out small phenolic compounds. If you don't want browning in your juice for a couple different reasons, and these are mainly stylistic in nature, you can talk to winemakers about their choices there. If you don't want that browning, you can add sulfur dioxide at press and crush. Another major culprit is lacase, and this is an enzyme that's only present in fruit that's been affected by vineyard rot, including botrytis. And one of the reasons that lacase is so difficult is that it's active throughout the life of the wine. Polyphenol oxidase, which is always present, it gets denatured by ethanol really quickly. And what that means is it becomes deactivated. But lacase doesn't have the same thing. So this enzyme can keep browning your juice and your eventual wine. So sulfur dioxide addition at crush to deactivate this enzyme is really important for wine quality in fruit that's been affected by rot. And sulfur dioxide maintains its relevancy despite some new pushback on health effects. And mainly this is because sulfur dioxide is the only wine additive that has both antimicrobial and antioxidant activity. There are compounds that we can add to our wine or that are naturally present in our wine that provide either antimicrobial or antioxidant properties, but no compound provides both of them besides sulfur dioxide. So I've put a couple examples below here. Ascorbic acid, this is also known as vitamin C. This is a strong antioxidant and can be used more frequently in fresh styles of white wine, but it's not an antimicrobial. Ascorbic acid is pretty great for certain forms of wine production because it binds directly with oxygen, but it has a dark side. If you use it in the complete absence of sulfur dioxide, it actually, ironically enough, can oxidize your wine. So it's a good tool to use in conjunction with lower sulfur dioxide levels, but it won't provide antimicrobial protection. Ethanol is a super great antimicrobial compound, and we're going to discuss this a little bit further in the presentation. The rules about sulfur dioxide, or I should say rules in a winemaking context, keeping our wine safe, those rules start to break down at high levels of ethanol, because the microbes that we're trying to combat are really heavily affected by higher levels of ethanol. It's a great sterilizer. Glutathione is also an antioxidant compound. It's present naturally in the grape, and it can also be added to wines in the form of different yeast nutrients and preparations that actually involve dead yeast bodies. So it's a tool that's used frequently in fresh styles of white winemaking. Dimethyl dicarbonate is also commercially known as Velcorin. It is the nuclear option for an antimicrobial compound, and it is used on bottling lines, so it's not dosed in pre-bottling. It's a very toxic compound, and those that administer it have to have a permit, and the wine has to go through a holding period where it can't be consumed by people because it is toxic. However, this compound breaks down into essentially nothingness, and it's a really great antimicrobial compound. Finally, phenolics are something that we don't talk about too much in terms of antioxidants, but those of you that follow health foods will know that phenolics are actually good for health, and one of the reasons they're good for health is because they're antioxidants. So really beefy styles of red wine, ones that have high levels of tannin, actually have quite a bit of antioxidant capacity. However, that doesn't mean that you can completely avoid the use of sulfur dioxide in all conditions, but it's a good backup. So to recap this section, sulfur dioxide is an antimicrobial compound, and it works against all microbes. However, certain microbes are more susceptible to the effects, and they're mainly spoilage microbes. Sulfur dioxide is an antioxidant, and it binds with hydrogen peroxide and prevents it from oxidizing the flavor compounds that exist in our wine. So an example of this is the oxidation of ethanol back to acetaldehyde that smells like bruised nuts or sherry, bruised apple, nutty, or sherry. And sulfur dioxide deactivates certain enzymes, and this is really important at crush or press if you're making a certain style of wine where you don't want juice browning. Now we're going to get into the chemistry aspect of this presentation, and we're going to talk about the different forms of sulfur dioxide, including free, bound, total, and molecular, and we're also going to talk about different legal limits and why. So, I'd like to apologize in advance because here come the chemical formulas. As I said earlier, you don't have to be an SO2 chemist to get through this. The reason we have this section is to develop your vocabulary and use the terms correctly to show that confidence to the examiner. So how is SO2 chemically formed? Usually this is through the addition of a sulfite salt into our wine. And this is usually potassium metabisulfite, or KMBS, and it's added as a powder dissolved in water, and then we can dose that into our juice or wine at different stages. So here's a little chemical formula here in red. KMBS with water forms potassium and sulfur dioxide. That potassium eventually is destined to go away during cold stabilization, and the sulfur dioxide will remain. The KMBS use may be restricted by local regulation, including things like organic certifications. For example, in the United States, you can't have added sulfites in your wines. So now imagine you, rock star winemaker and master of wine student, goes to add some sulfur dioxide to your barrel of wine. So you've got your little pitcher, you've figured out how much sulfur dioxide you need, and you've mixed it up with a little bit of cold water, and you're going to add it into this barrel. What's going to happen is the sulfur dioxide that you add is going to split into a couple different forms. There's going to be the bound form, the sulfur dioxide that starts reacting with stuff in the wine and binding to it. Usually this is acetaldehyde, which is the oxidized flavor in wines. This is more common in white wines. It could react with sugar and bind to it. This is common in sweet wines. Or it can react and bind to a tannin, which is more common in red wines. A portion of that sulfur dioxide is going to be free in the wine, and a portion of that free SO2, actually a very large portion of it, is in a form called bisulfite, and we're going to talk a little bit about that in a second. A very small portion of that free goes into a very powerful form called molecular. And altogether, all of the sulfur dioxide that you added adds up to the total sulfur dioxide, the total amount that you added. So starting out easy with the bound sulfur dioxide. So this is sulfur dioxide that's present in your wine, but it's bound to other compounds. So this is usually sugars, phenolics or tannins, or aldehydes, things that smell like oxidized aromas. So generally, when wine compounds are bound to sulfur dioxide, they become flavorless. That's not true for sugars or phenolics, but for things that you can smell, like oxidized aroma or butter flavor, those become flavorless. This form of sulfur dioxide, the form that's bound to stuff, is less active to completely inactive as an antimicrobial or antioxidant. So it's already basically done its job and bound up to something. Winemakers don't really care that much about bound sulfur dioxide because it's not going to impact their microbial stability or their antioxidant capacity of their wine. So many small laboratories and small wineries are not actually set up to analyze bound sulfur dioxide. We'll talk more about bound sulfur dioxide in the context of total sulfur dioxide in a second. This is much more relevant for people who are making sweet or dessert style wines. And now into the meat of it, the free and molecular sulfur dioxide. So free is the form with antimicrobial and antioxidant properties, and this is really the form of sulfur dioxide that's actually providing the stabilization in the wine. The vast majority of this is in its little bisulfite form of free SO2, and that is a word that's important to us on the science side of things, but you don't really need to know it for your Master of Wine studies. Just know that that's the form of SO2 that's not the molecular. And then a very small portion of our free SO2 is in a form called molecular. And this is the most powerful species of free SO2. So it's the most active portion, and it's actually a sulfur dioxide gas. And it's in a pH-dependent chemical equilibrium with other forms of free SO2, including that bisulfite. So what in the fuck does that mean? The key idea is that molecular SO2 is free SO2. It's not bound to anything, it's just in a gas form that's very active. And the proportion of the free SO2 that's in a molecular form depends on the wine pH. So lower wine pH means more molecular SO2, which means more active SO2 actually doing work in the wine. Implications of pH on sulfur dioxide. This is important to think about different wine styles or concerns for winemakers. Lower pH wines require less free sulfur dioxide. So a larger slice of that free sulfur dioxide is in that gas form or molecular form, and it's doing work. Work being killing off bad microbes, work being preserving freshness of aromatics by working against oxygen. One of the problems on the other side is at high pH. So in this, for wine, I would define high pH as pH higher than 3.7. And these kind of levels of pH are increasingly common in New World or riper styles of wine. So once we get into that zone, it becomes nearly impossible to actually produce that molecular sulfur dioxide. So you still have free sulfur dioxide present, but it's not going into that tiny, really active slice that's doing the work. So winemakers have to rely on other antimicrobial or antioxidant compounds in their wine instead of sulfur dioxide. So I'm going to show you now two real examples of the impacts of pH on molecular sulfur dioxide. Our first one here is a low pH Riesling. So this is the 2016 Dönhoff, I can't pronounce that, Oberhauser Leichenberg Riesling Cabernet. My father would not be impressed with me right now with that German pronunciation. So, it's at pH 297, which is really quite low for a wine. When we see pH numbers like that, they pretty much exclusively are in German Rieslings or cool climate sparklers like Champagne. This wine has a free sulfur dioxide level of 31 milligrams a liter and a molecular level of 2.01 milligrams a liter. So you can see how small that slice is. 6.5% of the free SO2 was in molecular form. So even though that molecular sulfur dioxide level looks really low, 2 milligrams a liter is very low. 2 milligrams a liter is actually the same level that you might even see dissolved oxygen in a wine. But it's very active. So this particular wine smelled like sulfur dioxide because such a large proportion of that free was in that molecular gas form. So if something's in a gas form, it's really easy for you to smell. So pretty much all of the compounds that are aromatic in our wines are escape the wine media and go into gas form so that we can detect them. So this wine really smelled like a matchstick. And this is a common trait in German Riesling, and it's mainly part of the style. So this winemaker has chosen to add a level of sulfur dioxide in the form of free that gives the wine a lot of stability and ability to age. But because the wine's pH is so low, a large proportion of that SO2 went into the molecular form and is aromatically detectable. And on the opposite end here, we have a high pH Cab Sauv. This is the 2015 Caymus Vineyards Napa Valley Cab Sauv. It is a pH of 396, which is on the upper end of high. It has a free sulfur dioxide level of 25 milligrams a liter and a molecular of 0.17 milligrams a liter. So only 0.68% of the free SO2 was in molecular form. If you remember the 6.5% of SO2 that went into molecular form for that Riesling, you'll notice that it's almost a 10-fold difference. So I think this is a really cool example here of what a single pH point can do. And I don't mean to demonize this wine in the slightest. This is a very stable wine that's designed for national and international distribution. And that free SO2 level is a very safe level so that when the wine ages and oxygen naturally goes through the cork, that SO2 level is high enough to be depleted. This wine underwent a sterile filtration. So this SO2 that's here in the wine, it doesn't have the burden of being an antimicrobial compound. All it has to do is act as an antioxidant over time. So this molecular level is low, but this wine is still stable. So a key idea to think about here is values are important, but they don't mean everything because SO2 is not the all or nothing thing that safeguards our wine. We have different modern tools, including, wow, I just completely spaced on a word there, sterile filtration, and other antimicrobial and antioxidant tools that we can use. A nice generalization that we can make about pH and sulfur dioxide and climate: cooler regions tend to have more acidity and thus they have a lower pH. So an example there, like that German Riesling, it had a pH below 3 and really active molecular SO2. So the SO2 was much more effective and much more ready to do work in our wine at an antimicrobial and antioxidant way. And on the opposite end, warmer regions tend to have less acidity and higher pH. And this is the same for wines that are made in an intentionally riper style. So they hang out longer on the vine, they have more sugar and thus more alcohol, they have lower levels of natural acidity and higher pHs. So these wines tend to have sulfur dioxide that's quite a bit less effective because of that pH. But the good news is that usually ripeness goes hand in hand with ethanol. So these wines have a good backup antimicrobial in the form of ethanol. So in my mind, I would think, okay, if that Caymus Cab had an ethanol level of 12.5 instead of the 14.5+% that it has, we'd be in a much more difficult position. But that wine was chugging along nice and easy in barrel because it could lean back on that antimicrobial protection that it had from ethanol. And another takeaway is that with modern technology, winemakers are less dependent on sulfur dioxide for wine stability and ageability, because in previous years, before we had sterile filtration technology, that was really the main thing that you would have to act as an antimicrobial or antioxidant in your bottle. But now, winemakers of all sizes have the ability to sterile filter their wines. So then, sulfur dioxide is only needed for color and flavor protection in the wine as it ages in bottle. So this is a good thing. It allows us as winemakers to rely less on sulfur dioxide. Here is a chart with different legal limits for total sulfur dioxide in major winemaking nations. This chart was adapted from Cornell University's Extension Agency. The reason I've included this chart is looking at the examiner's report for these kind of questions involving sulfur. They're asking students to have an understanding of the different legal limits in different countries. And this is a really interesting chart because many countries make a differentiation between sweet wines, white wines, and red wines. And this is important from a winemaking perspective. So let's take a look at the European Union. They have a really great comprehensive list here, and they break down their different wine styles and give them different total sulfur dioxide limits. And this makes a lot of sense from a winemaking perspective. So you can take a look here, and the white or rosé styles of wine that are less than 5 grams a liter of residual sugar, they have a legal limit of 200 milligrams a liter. For those same red wines, the styles that are dry reds, have a limit of 150, so it's lower. And if you remember before the discussion on other antioxidant compounds in wines, tannin's one of them. So red wines tend to require less sulfur dioxide. Additionally, when we add sulfur dioxide to a red wine, what happens is the sulfur dioxide goes into the wine and part of it binds to the tannins. And then as the wine matures in barrel or tank, those tannins knit up into long chains and eventually precipitate out of the wine. So they drop off. And that sulfur dioxide that originally bound up to them goes away as well. So when you continue to add sulfur dioxide to red wines during the winemaking process, the free can go up, but the total doesn't go up by a huge amount. In white and rosé wines, we don't have those same style of tannins. So what happens is we keep bumping up our sulfur levels to provide stability during the aging process, and part of those sulfur dioxide that we add goes into a bound form with acetaldehyde or sugars, but those compounds never drop away. So the total sulfur dioxide continues to climb up. And the European Union has recognized that this is happening, so they've made their legal limits different for red and white. And you'll also see here that for sweet wines in the EU, things that are higher than 5 grams per liter of residual sugar, they've bumped up their legal limit by 50 milligrams a liter. And they're recognizing that sulfur dioxide is binding to sugars in those wines and that they need more sulfur dioxide. And this is really clearly illustrated here in some of the EU-specific wines that have even higher levels of sulfur dioxide limits. So, on the real top end here, looking at the Beerenauslese, Trockenbeerenauslese, and ice vines, you can see that they have a legal limit of 400 milligrams a liter, which is really high. And the reason for that is because these wines have so much residual sugar. And I'm going to give you a little example here on the next slide. So this sulfur dioxide, when we add it, it binds up to sugar. So imagine you are making a nice sweet wine in the European Union, living it up in Sauternes. So we're taking our Semillon and Sauv Blanc and we're gently hand harvesting it with its botrytis infection. So the fruit is pressed, and remember that lacase enzyme, the one that browns things out in rot infected fruit, it starts to brown our juice very heavily. So we add a little bit of sulfur dioxide to deactivate that enzyme and prevent the browning, and that sulfur dioxide binds to sugar and becomes bound SO2. That juice is then fermented until it naturally stops, and the winemaker adds sulfur dioxide to provide antioxidant and antimicrobial protection, and some of that sulfur dioxide stays free and does work in the wine, but most of it binds up to that high level of sugar and becomes bound sulfur dioxide. And then when the winemaker's finishing the wine and they're ready to bottle, the winemaker is adjusting that sulfur dioxide to a level that provides ageability that's expected in this classic sweet wine. So they're adding more sulfur dioxide to provide antioxidant and antimicrobial protection. Some of the sulfur remains free and most of it binds, just like all those other stages. So in the end, our modest level of free sulfur plus our very high level of bound sulfur adds up to a very high level of total sulfur dioxide. And that's just the nature of making sweet wines. Here are some really great illustrative examples of those sulfur dioxide levels in sweet wines. So we have a 2003 La Ferie Paraguay from Sauternes. And this is an older wine. I had this wine analyzed this year in 2019. So it's 2003. And it had a free sulfur dioxide level of 12 and a total of 232. Comparing that to a newer wine with less sugar, the 2012 J.J. Prum Wiener Sonnenner Riesling Auslese from the Mosel has 24 milligrams a liter of free and 174 milligrams of total. And then comparing it to a fresh, not sweet wine, we have the 2016 Germain Sauv Blanc from northern Italy. It has a free sulfur of 14 and a total of 87. So we can see some trends here. The wine designed for the quickest consumption with the least amount of sugar has the lowest level of both free and total sulfur dioxide. Those two sweet wines have significantly higher totals because the sulfur dioxide that the winemaker added bound up to the sugar that's present. And additionally, both of those wines are designed for further aging, so the winemaker wants to retain a decent amount of free sulfur as well for freshness. Let's move on to some practical stuff to discuss what's happening in the winery, and we can play winemaker for a little bit here. Here is a reminder of what's happening in the winery. This is a nice diagram from Jackson's wine science book showing the diversion of flow between white wines and red wines. So just a reminder for everyone, white wines are pressed before fermentation and rosé wines as well. So here are the stages in red winemaking when we want to consider sulfur dioxide. Firstly, during harvest, this is mainly for antimicrobial protection, and the amount that we add depends on the rot level and the transport time between the vineyard and the winery. So dosing in sulfur dioxide can be quite standard for machine harvested fruit. It's less common for hand picking because the bins for hand picking are significantly smaller and the fruit doesn't get crushed up. So we don't have skin or juice contact where microbes can thrive. In machine harvesting, especially on machine harvesters in area where we do have disease pressure, liquid SO2 can be dosed into bins on the machine harvester. The second stage is crushing or destemming, and again, this is for antimicrobial protection. The level that the winemaker can add is really based on the rot level. I'm making wines here in Washington in the United States, and though most people think our climate might be more like our major city, Seattle, we're actually out here in the desert with low levels of rock pressure. So I add between 0 and 25 milligrams a liter of sulfur dioxide at crush. However, on a Chardonnay, this is a different example, not from red winemaking, in a very cold year, I've added over 100. And that was in fruit that straight up had rot on it. It did have gray mold. So more info on the crushing and destemming. Most of this addition is going to be bound up by sugars or bound to the bodies of microbes. So what happens is we're adding sulfur dioxide in here, but it's not making its way through into the ferment. There's so much chaos that's happening chemically during this stage that sulfur dioxide, if we measured it a day after we added it, we'd probably see 0 free and maybe close to 0 total as well. During cold soak, if a winemaker chooses to undergo this step, they could also add sulfur dioxide for antimicrobial protection. And this, again, based on the spoilage risk. Usually we don't want to add more than 50 milligrams a liter. If we're adding more than that, we start risking having that sulfur dioxide travel through into the ferment and inhibit our preferred Saccharomyces cerevisiae. So you can see here under the Ys, our red winemakers are less concerned about antioxidant activities at all stages of production when compared to white or rosé winemakers. And this is because during the crush process, there are not many free aromatic compounds that can actually be oxidized. And during aging, tannin is a good backup antioxidant. Moving on to post-malolactic fermentation. This sulfur dioxide is added for antimicrobial and antioxidant protection, and it may also bind up to that acetaldehyde bruised apple aroma that developed during malolactic fermentation. A winemaker usually bumps up their level to a target 30 or 40 milligrams a liter of free sulfur dioxide, and they attempt to maintain these levels throughout the aging process. Barrels or tanks are going to receive a regular addition based on the winemaker's style or goals. So an example is barrels can be topped monthly or quarterly. I know a winemaker locally here that tops weekly. So that has positive aspects and negative aspects. One of the positives is that she's always retaining a really nice level of free that she wants. The negative is that she's getting into that barrel every week, and the more you get into the barrel, the more chance of contamination you actually have, and the higher levels of oxygen ingress as well. So different strokes for different folks. During racking and filtration, we're also adding sulfur dioxide as an antioxidant. During that racking and filtering process, you can lose up to 20 milligrams a liter of free sulfur dioxide just as oxygen enters the wine, forms hydrogen peroxide, and binds up with that free sulfur. So you're going to have to replenish that sulfur dioxide. During pre-bottling procedures, we're adding this as an antioxidant. We want to achieve the required level for the bottled product. And usually we want to achieve a target molecular or free value. And that level depends on the winery, the market, the ageability, and the style. So again, there's no one way, but in general for red wines, we want to get to 0.5 milligram per liter of molecular or about 35 milligrams a liter of free. So to go back to that Caymus Cab example from earlier on, they weren't reaching that target molecular because they had such high pH, but their free sulfur dioxide levels were completely in line with a really stable bottled product. And the reason that we're doing this is that free sulfur dioxide is going to bind up with oxidation products that form during our bottle aging as oxygen goes through our screw cap or our cork. So that sulfur dioxide is going to provide protection for our aromas, flavors, and color. And you may be thinking to yourself, what about fermentation? We went directly from cold soak to post-malolactic. Winemakers do not want to add sulfur dioxide during primary or before malolactic. If they add sulfur dioxide during primary, that SO2 goes directly into the yeast cell and is transformed into hydrogen sulfide, or H2S, and that has a really distinct rotten egg aroma. And if a winemaker adds it before malolactic fermentation, they can inhibit their malolactic. This may be desired in a lot of different styles of white, but usually not in red. So a level of 10 milligrams a liter of free is sufficient to inhibit malolactic fermentation. So we don't consider those levels, or we don't consider adding sulfur dioxide at these stages. Like I said before in the pH consideration section, it's nearly impossible to maintain sufficient molecular SO2 at high pH, which is north of 3.7. So free SO2 is in a non-molecular form is still present and active in the wine. So it's acting as a decent antioxidant, but that molecular SO2 form, which is the gas form, it's a really good antimicrobial, because once it's in that small teeny gas form, it can slip right into a yeast or cell or a bacteria cell and kill it. So these high pH wines, they still have decent antioxidant activity, but they don't really have strong antimicrobial activity from their sulfur dioxide. Dr. Steve Price is the phenolic chemist for ETS Laboratories based out of St. Helena, California, and he's a really excellent resource. He says that levels above 40 milligrams a liter of free sulfur dioxide can inhibit phenolic maturation in reds. And basically, the key idea here, and this is an advanced topic for another time, is oxygen is the key thing that knits together tannins. It's actually that oxidation product acetaldehyde that forms the glue that turns small astringent tannins into longer, more rich tasting tannins. So if you have high free levels of sulfur, you're knocking down your levels of acetaldehyde, and therefore you're slowing down the maturation of those tannins in barrel. This is a dangerous situation, though, because you don't want to go at a very low level of sulfur dioxide in the hopes of having quick maturation of tannin, because then you open the door to the spoilage of your wine. So to find a nice balance, he recommends between 30 and 40 milligrams a liter for ideal microbial inhibition and phenolic maturation in red wines. Moving on to white and rosé winemaking. During harvest, we're adding sulfur dioxide for antimicrobial and antioxidant protection, and just like the reds, it varies based on rot level and transport time between vineyard and winery. For crushing and destemming of our white fruit, we're also adding it for antimicrobial and antioxidant protection, again varying based on rot level. And things start to divert here between our whites and our reds at the press stage. We're adding SO2 at the press mainly for antioxidant reasons, and actually something that I forgot to include here is also anti-enzyme. So it's preventing those browning enzymes from working in our wine. The level that our winemaker would add here really varies based on style and variety. And an addition of sulfur dioxide at the press may not be required if they added a sufficient amount of sulfur dioxide directly before the press during the crushing process of the fruit. So we would add more if we wanted to inhibit juice browning and phenolic oxidation. Two examples here. If you were making a Chardonnay, there is I'd say it's a trend, but actually it's an old style technique that's now gaining traction again, and it's called browning or blacking of the juice, and that's allowing all the phenolics in the Chardonnay to oxidize at the press, and the juice comes out actually looking like coffee. That's really what happens if you actually allow the browning process to go all the way through. It doesn't even look like juice anymore. But because you've oxidized all of those phenolic compounds, they've bound up together and they've dropped out of the wine. And what you can actually get is a much smoother tasting, less astringent, and ironically even more optically clear style of Chardonnay. On the opposite end of that spectrum, if you're making a New Zealand style of Sauv Blanc, they like to really protect the press. So this involves the use of sulfur dioxide to prevent browning and the use of inert gases, including carbon dioxide, to prevent oxygen contact in the first place. One of the reasons that this is so relevant for Sauvignon Blanc is because Sauv Blanc, the aromatic backbone of varietal character there, is really easily impacted by oxygen, more than actually any other variety out there. At least I should say any other international variety out there. So having dissolved oxygen, or oxygen that's present in our juice, can actually impact the aromatics as they develop in the wine. So that's why New Zealand Sauvignon Blanc, or New Zealand Sauv Blanc producers pioneered this reductive style of pressing with more sulfur dioxide. So moving on to post-primary, we would add sulfur dioxide as an antimicrobial to inhibit malolactic, as an antioxidant if we wanted to add a certain amount to bump it up for cellar aging. Usually our target here is about 0.8 milligrams per liter of molecular. During racking and filtration, it's the same deal as the red wine. We want to replace the sulfur dioxide that was lost. And during pre-bottling, we're going to add sulfur dioxide again as an antioxidant. So same deal as the reds. We're looking to achieve a target, and that target can change based on winery, market, and ageability. Usually for whites, the target is 0.8 milligrams per liter of molecular SO2. I should actually say that's for a dry white. You would be above 1 milligram per liter of molecular if you were dealing with a sweet white. And we're adding it for the same reasons as the red. That free sulfur dioxide is going to bind up with those different oxidation products during the aging process, and it's going to preserve our aromas, flavors, and color. So the reason I mention color here is that's pretty relevant for rosé winemaking. We do have free anthocyanins that are present in our rosé, providing that nice pink color. And if they oxidize in bottle, they can go towards a more light brown color that may be unappealing to the consumer. So the key differences between the red and white or rosé styles of production: red wines have tannin as an antioxidant and usually more alcohol as well, so that acts as an antimicrobial. They just need less SO2 support. White and rosé wines need a higher level of free SO2 during aging and at bottling to combat microbes that might be present at lower ethanol and to retain the freshness of aromatics. And what about fortified wines? The rules are pretty much right out the window when we're dealing with fortified wines for a couple different reasons. One is ethanol is a super great antimicrobial compound. Almost all yeast and bacteria are inhibited over 16% alcohol, and really things drop off precipitously around 15. And many fortified wines have an intentional style of oxidation, and we don't want to cover that up because that's key to the style. So these rules that I mentioned before for reds, whites, and rosés, don't think about them for things like red ports or white ports or different things like Muscat Baume de Venise as a white wine. Don't think about them like that. Think about those previous rules for dry whites and dry or off-dry whites and rosés. I wanted to include this slide about SO2 in relation to a couple different topics because the questions that I mentioned from the previous exams, I only grabbed those questions because they directly addressed sulfur dioxide in the question. Sulfur dioxide is important to consider for quite a few different questions that are on the exam. So questions involving HACCP, which is hazard analysis and critical control points. Those are the when stages that I mentioned before on those red and green tables for additions and why. So those are the critical control points for SO2 monitoring and adjustment. Winemakers could have HACCP plans for sulfur dioxide. Closures. So this could be addressed in bottling and packaging questions. 1 milligram a liter of dissolved oxygen depletes 4 milligrams a liter of free sulfur dioxide. That's a really great thing to think about during bottling and selection of closure. Closures with lower oxygen transfer rates, or OTRs, will require less SO2 to age for the same period of time as other wines with other closures. And that's because less oxygen is getting into the wine and it's depleting less of the free sulfur dioxide. At bottling, free sulfur dioxide should be monitored as an indication of oxygen pickup on the bottling line. So an example here, not mentioning any wineries, is that if you're bottling, you would grab a bottle for beginning, middle, and end of the run. And if you see the free sulfur dioxide levels start to deplete over the course of the run, you can infer that you have oxygen pickup, and usually that's from a pinhole-sized hole inside one of the hoses that's delivering the wine from the bottling tank to the bottling line. A lab manager or a lab technician, or a quality control manager, if they saw the oxygen level go down during the bottling process, that's a flag to go in and stop the line. Because you don't want to get to that end of that run and have no free sulfur dioxide in your wine, and you have wine that's not ready to go to market and has to be destroyed or unbottled. So now let's go full circle again and look at some of those theory questions from the beginning of our presentation, and I've included some information from the examiner's reports. So, explain the recent changes in use of sulfur and sulfur dioxide in the vineyard and cellar prior to the completion of malolactic conversion. One of the things that the examiner's report said is that the candidate needed to have a solid knowledge of legal and permissible levels of sulfur and SO2 around the world. So get to know that table. Reductions in total used, less frequent use, alternatives, including picking at night to keep fruit cool rather than by day when hot picking required sulfur as an antiseptic, and earlier harvest to maintain acid protection should have been considered, along with the flip side, the inherent risk in reduced sulfur. So go back to that table about the critical control points for sulfur dioxide additions, and take a look and remember why we're adding sulfur. So I've added in a little bit of commentary here. If I was answering a question like this, I'd start to think about ways that a winemaker could provide antioxidant or antimicrobial protection without sulfur. So, like that examiner's report said, harvest at night. The cooler nighttime temperatures mean that there's less microbial pressure. Almost all chemical reactions and microbial growth increase at higher temperature. So when we harvest during the day, it's providing when we harvest during the heat of the day, it provides a better environment for microbes to grow in. One thing that I want to dispel is that harvesting at night does nothing to retain acidity, but it does a lot to provide an environment that's less conducive to microbial spoilage. We could harvest earlier or perform a legal acid addition to lower the pH to provide more molecular sulfur dioxide, which is more effective. And that would lower our spoilage pressure as well, because spoilage microbes don't like that lower pH. This can run up against style. An example here is that in some areas of the world, including my beautiful little corner over here in Washington, have high pHs, and sometimes the distance that we need to travel in terms of pH points is just too far to do it with a legal organic acid add like tartaric or malic. If we added the amount of tartaric or malic that was required to get to a target of lower pH, our wine would taste really sour. So frequently we just have to let it ride. So that's an argument against that use of acid add. However, it works perfectly well in certain styles. Again, in my corner of the world, I've added acid to Riesling. Alternative antioxidants and protective measures can also be used. So think about ascorbic acid or additions of glutathione. So that's that small peptide compound that can be present in different yeast nutrients. You could use carbon dioxide snow during processing to keep oxygen off of the juice and therefore lower the need for an antioxidant compound. You can run your cellar colder to reduce microbial pressure during the aging process. So on the other side here, they wanted people to address risks, inherent risks to low sulfur. Volatile acidity can be formed by all sorts of different microbes that gain a foothold at crush, and that's a good topic for a totally different presentation. I think that I might have a wine microbiome one coming up sometime soon. Moving on to another question. Consider the implications of reducing levels of sulfur dioxide in the post-malolactic conversion, handling, and bulk storage of still wine. So we've basically got a dry still wine. Actually, no, it doesn't say dry wine, or it just says still. So we've got a post-ML wine here. And they say this is a technical question which required a technical answer. For a question around a core part of the Paper 2 syllabus, this prompted few convincing answers. Oh, burn. Very often answers tended to lapse into a general account of the use of SO2 in maturation. The question required a structure that enabled the implications of reduced levels of SO2 to be properly addressed. Stronger responses firstly defined terms, sulfur dioxide, its role, and usual dose rate with accurate levels quoted. So get familiar with those milligram per liter numbers that I had earlier. And also define the post-malolactic period. This might be followed by an identification of the risk associated by a reduction of SO2 levels during handling and storage. An examination of the advantages as well as the disadvantages of reduction of SO2 levels would present a balanced argument. There were many good uses of examples, but too often responses did not answer the question itself. So, they want you to define some terms. So, sulfur dioxide, you can go back to the beginning of this lecture, but define it as an additive. Its role as an antioxidant and antimicrobial. I haven't included its role as something that deactivates enzymes because that's not relevant for this style of question because they're asking for post-malolactic here. They're asking for usual dose rates. So this would be additions of various doses to achieve a target value, usually something between 30 and 40 milligrams a liter of free sulfur dioxide, or maybe you could quote some of those molecular sulfur dioxide levels, like 0.8 in white wine or 0.5 in red wines. Post-MLF bulk storage, so these are wines that have undergone malolactic fermentation, but they have not been prepared for bottling, so these wines have not been sterile filtered, and they probably haven't been fined as well. There's some risks here, including Brettanomyces. This is something that I hadn't mentioned before, but Brett can be an issue in post-malolactic wines, especially reds. And Brett is actually really quite resistant to sulfur dioxide. It has more of an issue to be pushed back by ethanol. Additionally, one of the key ways to fight Brett is by cooling down a cellar. Another risk is oxidation. If this is a wine that's not been very well handled and it's not being checked in on frequently, there could be oxidation in barrel or tank because the tanks or barrels aren't topped up frequently enough. So that can cause different things to form on the top of the wine, including acetobacter. One of the advantages of lowering your sulfur level could be more rapid phenolic maturation in red wines. Our next question, many winemakers are reducing the levels of free and total sulfites in wine. Consider the role of sulfites at bottling and until the wine reaches the end consumer. What are the implications of reduced levels of free sulfites? So looking at some points from the examiner's report, they were actually really comprehensive here. They wanted the key points of understanding to be the risks arising at bottling and continuing until the wine reaches the consumer. They wanted the student to address the 4 distinct properties of SO2. And I take some issue with this. However, it doesn't really matter what I think because ultimately we're trying to pass an exam that is being reviewed by this examiner. They say the 4 distinct properties of SO2 are antioxidant, antimicrobial, antioxidasic, and less importantly, binding with acetaldehyde. I take issue with the antioxidasic piece here because oxidizing enzymes are present earlier in the fermentation, or excuse me, the crush and fermentation process, and they're inhibited by ethanol. Oxidizing enzymes should not be at play at bottling or in finished wine. And they actually say it's less important for binding with acetaldehyde here, but I would actually say that's relatively important because aldehyde could be produced in low SO2 environments once the SO2 in the finished wine is depleted and oxygen is entering the wine through the cork or screw cap. They wanted you to focus on the role of SO2 at bottling to the end consumer and the implications of lowering the level of free sulfur dioxide. Examples or ideas including the wine not being in drinkable condition or developing prematurely or developing faults such as microbial fermentation in bottle. The role of free and total sulfur dioxide in various wines, including numbers. So I would go back to those slides in the chemistry section and taking a look at the differences between free and total. And then thinking a little bit about sweet wines and those total SO2 values or legal limits in different countries. They also wanted you to address the potential risks to health and high levels of free SO2 and consumer concerns about additives, especially since requirement for obligatory sulfite labeling. Lower levels may improve aromatic expression in young wines. So the health risks is a little bit out of my scope here. That's not exactly a chemistry question. However, aromatic expression in young wines is really relevant. So in my town in Walla Walla here, we have a small winery named Figgins Family Wine Estates, and they are in the ultra premium to icon levels of wines. And they also make a rosé for their wine club only, which they bottled this year in 2019 at 10 milligrams a liter of free sulfur dioxide. And their goal for that was aromatic expression right away in the rosé wine because it was going directly to their wine club customers. It doesn't go to wholesale, it doesn't go to multiple markets, it basically goes just direct to consumer through the wine club, and they wanted it to be expressive right away. Natural wines made with no added sulfur dioxide or very little, and consumers for such wines may have a higher tolerance for what some might see as faults. So there are some actual real concerns about less sulfur dioxide, and I would say that these in natural wines actually occur earlier in the process than at bottling. But if you remember that sulfur dioxide table, pretty much every country but the US can add sulfite to their natural or organic wines, but the US can't. So that might be something to include. That's a really massive question. And I actually think we need a standalone SO2 at bottling lesson to really address this question. And my takeaway from these exam questions is that you don't need to be a chemist. Know the basic functions of sulfur dioxide, those 3 or 4 different functions. Know the critical control points and the target levels at those points, so going back to those tables, and knowing the legal limits in multiple countries. And I'm brushing up on my examples on reduced SO2 use because all of those questions asked about reducing sulfur dioxide levels. So I hope that this presentation helped a little bit. If you're feeling a little bit like my kitty on the left before, having a little bit of a panic, wondering what in the fuck is actually going on, maybe afterwards you could smell a wine and note that the wine was bottled 2 months ago and is highly aromatically expressive, and you can see the intent of the winemaker in bottling at lower levels of targeted molecular SO2 in wines intended for quick to market, maybe. So what's coming up next? pH and acidity? Enzymes? Something else? SO2 at bottling? Holler at me. Thank you very much, and happy studying.